Hi, everyone. My name is Frits. I'm a PhD student here at CQT. So today I'm going to talk about entanglement and non-locality. And I think this might be the most weirdest part of quantum mechanics because it's really different than something you're used to in real life. You cannot really compare it to anything that you see happening in everyday life. So I think that's why it's pretty interesting. And it also has some applications to cryptography and other things. So yeah, for entanglement, we always talk about at least two or more particles that are somehow very much connected. So they are more connected to each other than anything that we know from class. So what you've seen before is one qubit, can be written in a base is 0 and 1. You can have superpositions, for instance, this one. So if you have in this state, you have a 50% chance of getting 0 and 50% chance of getting 1. So now what happens if we have two qubits? So say we call one qubit A and the other B. Then for the qubit A can be in 0 and 1, and the qubit B can also be in 0 and 1. But then we have to form a Hilbert space for our two qubit system using the tensor product. So the tensor product is this time symbol with a circle. And if we write down this 0 tensor 0 with the subscripts A and B means that the qubit A is in state 0 and qubit B is in state 0 as well. So another short way to write this, and we will do this from now on, is we will just write 0, 0 and omit the A's and B's. So this meaning that the first position represents the first qubit A and the second position represents qubit B. And then we have three other possibilities. 1, 1, 0, 1, and 1, 0. Together, these form the Hilbert space of our two qubit system. Okay, so now let's look at this interesting superposition. We will consider this state a lot during this lecture. So we have a state of two qubits, and it is simultaneously in it's in a superposition of 0, 0 and 1, 1. So let's think about what this means if we have two qubits in this system. So for instance, say that one of the qubits is on Earth and the other qubit B is on Mars. Now the distance between Earth and Mars is very large. It takes about 15 minutes for light to travel from one to the other. So that also means that any information will also take at least 15 minutes to get from Earth to Mars or vice versa. So there can be no information transfer that happens immediately. You always have to wait at least 15 minutes, right? So now, say we have qubit A on Earth, qubit B on Mars, and then we do a measurement simultaneously on Earth and Mars. We do the same measurement, or we perform a measurement on the qubit we have there. And then what we can get is we have either a 0 on Earth and a 0 on Mars, because that's one of the two possibilities in the superposition. Or we have a 1 on both Earth and Mars. But now this is interesting because we do this measurement at the same time. So how is it possible that if you do, so if you do the measurement on Earth and you get a 0, then you immediately know that the measurement on Mars will also give a 0. But that means it seems like information has traveled immediately from Earth to Mars that way. So this is why Einstein said, this is not possible, quantum mechanics cannot be correct, it's spooky action at a distance. But actually, if you think about it a bit more, it's not that spooky because you're not sending any information. So I said information can travel at most by the speed of light. But if you think about this, there is no information being transmitted because you have a 50-50% chance of getting a 0 or a 1. And you cannot choose if you get a 0 or a 1. So you cannot use this system to send a bit from Earth to Mars because the bit is just random. All you know is that Earth and Mars will have the same bit. They will both have 0, both have 1. But you cannot choose if it's 0. So that's why you're not communicating faster than the speed of light. So it's still okay. But however, I mean, these two systems are highly correlated. And with correlated, I mean that they're both 0 or they're both 1, right? So now let's get into the mathematical definition of entanglement. So we say that a state, psi, is separable, is not entangled, if you can write it as the tensor product of two states. And then we say that it is entangled if you cannot write it. So for example, if you look at this state, this is a separable state. So we have qubit A in a superposition of 0 and 1, and qubit B in a superposition of 0 and 1. But now, if you were to measure qubit A, you would get 0 or 1 with a 50% chance, but then you don't know what qubit B will be. So you see here that there is not really a connection between A and B. That's why we would call this state not entangled or separable. And then this interesting entangled state, this state is entangled. And you will show this later this afternoon in a tutorial that you cannot write this state as such. Tensor product. Yeah, so as we saw, if you have an entangled state like this, then measuring one qubit immediately affects the state of the other qubit. It will assume the same state that the first qubit was in. So in 1935, Einstein, together with Podolsky and Rosen, said that it cannot be true. Quantum mechanics is incomplete. So with incomplete, he meant that although quantum mechanics is correct, so quantum mechanics does predict you get a 50-50% chance of a 0 or a 1. That's correct. But it's not the whole story. There must be some hidden variable that tells you if it's going to be hopefully be 0 or both 1. But it's just that the theory is not complete. And somehow nature does, so these particles, they do have a hidden variable before the measurement is done, saying if they will be 0. But there's no such thing as a superposition. But that was just theoretical. And at that time, it was really hard to do any experiment, because if you want to do an experiment, you have to control these very small particles, which they couldn't do in 1935. A bit later, in 1964, Bell came up with an actual experiment that you could do to test the prediction of Einstein, Podolsky, and Rosen, EPR. But it was still hard at that time to do this experiment. So later, Clauser, Warren, Flamini, and Holt, in 1969, they improved on Bell's experiment, and they came up with a CH-SH game. And this proved to be a really nice experiment that they could actually perform. And they performed this experiment, and it actually confirms that quantum mechanics is correct, and that Einstein and friends were wrong. So in this lecture, I want to explain the CH-SH game. And we will also play it here in the room. And after that, I will explain what it means. So this is the game. We have two players. We call them Alice and Bob. And they both get an input. They get an input bit X and 1. So Alice gets X, which is either 0 or 1. And Bob gets a Y, which is also 0 or 1. And then they have to come up with an output bit. A. So Alice gives an output bit A, and Bob output bit B, which is -1 or +1. So note the difference. The input is 0, 1, and the output is -1. The way that Alice and Bob have to come up with their output, A and B, they can determine themselves. So they have some process, some strategy of giving an output. Now, what is the goal of this game? Well, it's a cooperative game. They both win or they both lose. They win. So most of the time they win when they give the same output. So when they both give +1 or they both give -1. But that's only when the inputs are 0, 0, 0, 1, or 1, 0. Right? So there are 4 different possibilities for the inputs. Right? And for these first 3 possibilities, we want Alice and Bob to get the same answer. Only in the case that both the inputs are 1, we want them to actually give the differing answers. So one gives +1 and the other -1. So if you were to multiply yeah, if you were to multiply the outputs A times B, if they're the same, then it always gives one, right? Because +1 times +1 is 1, and -1 times -1 is also 1. So that means that A times B is 1. And if they differ, if A and B differ, then the product is going to be -1. So this is what we want. This is basically the game. Important is that Alice doesn't know what Bob's input is, and vice versa. So Alice only gets X, but she doesn't know Y, and Bob only gets Y, doesn't know X. Also, they can use something that we will call a source, which is basically anything. So they can use some external source to determine their answer. For instance, they can both look at the sun and then do some measurements, like the intensity of the light of the sun, and then use that to determine whether they get a -1 or a +1 as output. But the important thing is that they both share the same source, right? So Alice and Bob do not communicate with each other, meaning that they don't know each other's input, but they can both look at the same source. So the source communicates with Alice and with Bob, but Alice and Bob, they cannot communicate with each other. Because if they were allowed to communicate, then of course they could just they could always win the game, right? Then they would tell each other what to do. Now they will not play this game once, but they play many rounds, and they want to win as many rounds as possible. And maybe they won't win every round, but they will try to maximize their winning. And a way to capture that is by looking at the CHSH value S. Let me explain what this is. So S is the sum of 4 different terms, where the last term S11 has a minus in front. For instance, the S01 term, what is it? It is the average of A times B for all the rounds where they get inputs 0, 1. Right? So you do this a large number of rounds, and for all the rounds where the input is 0, 1, you check what Alice and Bob gave as output, and you multiply it together, A times B. And then the average of that is S0. So let's see, X0, Y1, that's this case. So you want A and B to be equal. So A times B should be 1. So you have to maximize S01. Because it's either -1 or +1. So in this case, you want this to be 1. That's why there's a plus in front of S0, 0, 0, 1, 0, because for these 3, you want them to be equal. And for this one, you want them to not be equal. So that means that you want the average to be close to -1. And that's why there's a minus here, because if the average is close to -1, this will be close to 1, minus S1. So, okay, so in the end, what you want is to maximize this value S. And if you think about it, the highest value you can get for S is 4. See how you can get 4? If you would win every round, then in these 3 cases, you would always get a 1. And in this case, you would always get -1. So if you have 1 + 1 + 1 minus -1, it's 4, right?
Are you only subtracting it to get rid of the negative sign?
Yeah, because the rule of the game is that you should not get the same output in this case, where the inputs are both 1, you should not. So in order to capture that, we minus there. Right? Because if you were to win this game every time, then S would be 4. And if you don't win it every time, it will be slightly less than 4. But so the goal is to get a high value of S. So does anyone have an idea how to achieve this? So you know the rules of the game. Alice and Bob are not. So we're going to do this game right now. So I want 2 volunteers, 1 Alice and 1 Bob. Your real name doesn't have to be Alice. And we'll do this about 20 times, 20 rounds, where you have to, Alice and Bob both get an input, write down an output, and then we'll see what S is. The goal is to get it as high as possible. So what do you think? Does anyone have an idea about some strategy to win this game. Does anyone know what happened if Alice and Bob agree to give the same answer every round? Say they agree, we'll both say 1 every round, whatever the input is. What is S going to be?
-4.
-4?
Wait, no.
No, 3. Anyone have an idea what happens if they output a 1 every time? What is S going to be? So, yeah, you're right. So if they output a 1 every time, they will win these 3 rounds. They'll always win it, right? And they will always lose this round because they don't give differing answers in this round. But the thing is, if they give a different answer, then A times, so if they don't give, so in these rounds, A times B will be equal to 1 instead of -1. Right, so this S11, the average will be 1, not 0, right? So if you lose this round every time, losing means that you get a +1 instead of a -1. That means that this average S11 will be 1. So it will be -1. So they will win these 3 rounds, 0, 0, 0, 1, 0. So these 3 S's will be 1, but this last S will also be 1. So you get 3 minus 1. So you get 2. So how can you get higher than 2? What if they just give a random output? They just randomly say +1 or -1. What would happen? Yeah, so we were thinking about what happens if they give a random output. What is the average of A times B going to be? A is the output of Alice, B is the output of Bob. What is it going to be if A and B are just randomly 1 and -1? If you multiply them together, the average will be 0, right? Because so A times B is either going to be +1 or -1. But if they just give random outputs, well, the average between -1 and +1 is 0. So the average of A times B will be 0. Which means that all these 4 S's will be 0. So the total value of S will be 0. And that's pretty bad, right? Because we saw we can get S's at most. And now we're only getting S's 0. Okay, so the strategy of giving random outputs is not good. But also the strategy of giving the same output every time. If they agree to output a 1 every time, it only gives you S is 2. 1 S is 4. So what can we do to get a higher S?
Your output S equals to 0 each time, because you don't get penalized if your output 0 for both X and Y.
Well, you output plus or minus 1. So not output 0, but the average could be 0, right? So if you output plus or minus 1, plus 1 half the time, minus 1 the other half of the time, the average will be 0, even though you cannot output it. So one thing that we didn't do is we didn't consider the source. So the source could be you guys shouting a number. So say Alice and Bob, later on we will have 2 volunteers, Alice and Bob, and then you guys could be the source. And the source is allowed to communicate with Alice and Bob. Source also doesn't know what X and Y is, but the source can shout a number. It could just say, write down +1, write down -1. Maybe that's a good strategy, because then what will happen is that Alice and Bob will always have the same output. They just write down whatever the source says. Is that a good strategy? So yeah, so if they just write down what the source says, we have a volunteer for Alice. Okay, so the idea is we'll have 20 rounds. I already have the input here. Now you're not supposed to see the input, but I think you cannot really see it. But so I wrote down the 1s and 0s as input for every round here, and then Alice or Bob has to write down his or her corresponding output, A or B, right? Who wants to be Alice? You just have to write down plus or minus 1. It's not that hard. So you're Alice, you're Bob. Maybe you should agree on some kind of strategy.
Okay. So Alice.
What are we doing? +1 or -1?
No, but even if we do that, we're still just gonna get like our S value of small.
Yeah. But it says the best
You want a source to do anything? We can like pick a random song every time or like. We can tell you our favorite foods or like.
You want a coin?
Should we do that? But then the thing is, we also talked about how the random kind of things would be. Good.
No, hang on. Let me.
Or you can share a coin.
Share the coin.
Share a coin. Share the same.
If we use the same coin, it's just gonna be the S equals to 2 things again, because we're just gonna be giving the same output.
Let's say both of you are doing different random coin. But what I'm proposing is to use the same.
Same coin.
Yeah.
How that work? So like, if it's heads, we get +1, tail, we get -1.
Yeah, both of you.
Yeah, but then isn't that the same thing? Like, if we're both doing the same output, like, if we're agreeing like, oh, tails, we do -1, then we both do -1 again, isn't it just the S equals to 2?
Yeah,
Yeah.
I think so.
Really?
Yeah. Yeah, if you give the same input every time.
So giving the same input every time is not an option. Can someone chat GPT?
No.
GPT is really bad with this kind of thing. It won't help you, no. But maybe you're lucky and we'll get higher than 2.
Anyone else come up with a strategy? Propose to our palettes involved.
Yeah, so what I'll do now is, so we have 20 rounds, so I'll just say round 1, round 2, round 3, and then when I call the rounds, you write down ±1, right? Because it has to be approximately at the same time.
What I'm thinking, could we do, let me say like a coin flip, we can try the same coin, but then we do the same, output only like 3 out of 4 times. Did that work? Do you wanna try that? I think maybe, possibly.
I'm not at this.
I know, yeah, I know.
So you're saying you flip a coin,
Yeah,
you say what the coin, if it's heads or tails,
Yeah.
or +1, -1.
so
and then-
what I'm saying is like,
You choose is if it's gonna be around where you do write it down or not.
so, okay. So like, let's say 3 out of 4 times, we're saying heads is +1, and then the last time we say, oh, heads is -1.
Flip it.
Yeah, so like every 4 things.
Every fourth, oh, so you mean round 4, 8, 12, etc. Yeah,
Try. We can
that sounds
try.
like a strategy. Let's just do that.
Alice, do you get that?
You will both get a +1 or both a -1. Oh, randomly, but you will still have the same thing that you write down. It's just kind of superposition was doing previously. Oh, it sounds okay.
Should we just?
Okay, sure.
Let's just do it and see what
Okay,
happens.
okay.
So heads is plus or minus.
So this one, when you see this one, is 1,
Heads.
and then the back, no 1 is 0. 0.
0. Isn't it
-1.
Yeah, it should be +1.
plus -1?
Yeah, so this is 1, right, $1, 1, and then the back, it's minus.
Maybe instead of saying heads or tails when you tell us what it is, can you just say like +1 or -1? So it's like.
Yeah, I'll just say plus and minus.
Okay, you will say +or -1, but then you guys have to remember every 4th round, you have to do the opposite of what he says.
Okay. Yes.
So he said, if he says +1, you write down -1. Round 4, 8, and 12, etc. Okay, round 1.
-1,
Round 2.
1,
Round 3.
1,
Round 4.
-1,
Round 5.
1,
Round 6.
-1,
Round 7.
1,
Round 8.
-1,
Round 9.
1,
Round 10.
1,
Round 11.
-1,
Round 12.
-1,
13.
1,
Round 14.
-1,
Round 15.
1,
Round 16.
1,
Round 17.
-1,
round 18,
-1,
round 19,
-1,
and round 20.
-1.
Okay, great. Can I have your sheets? I will calculate this using Excel.
Advanced technology.
Yeah, it will take 2 minutes. Have a short break. So I already have the inputs that you guys had, and now I'll obviously enter this. S is exactly 2.
Wow.
Exactly 2. Okay, that's a coincidence, but that's exactly actually what we predicted, right? Because we said if you guys both write down the same number every round, yeah, you get 2. Okay, yeah, so we got 2, which is actually, yeah, we could have expected that. Why again? Well, if you get the same answer every time, then the average of A times B will be 1 every round. So all 4 of these will be 1, so you get 1 plus 1 minus 1 is 2. So that wasn't that good. Okay, so you already know S can be at most 4 or at least -4. But what we will show is that actually under normal circumstances, which we call local realism, which is this room, for instance, S cannot be more than 2. So that means that whatever strategy you guys came up with, whatever you did, you can never get more than 2 in this game. So actually what you guys did was already the best you can do. Just giving the same answer, giving the same output every time. We'll give you 2, and that is the best you can do. And I will show that in the next slide. But using quantum mechanics, you can get a higher value for S. You can get 2 square root of 2. And I will also show how that is possible. So what is local realism? So this goes back to the paper by Einstein in 1935, where he said quantum mechanics has some hidden variables because he thought nature was not probabilistic. So probabilistic, you often hear that about quantum mechanics. It means that the measurement outcome is not determined before you do the measurement. So only when you do the measurement, then the qubit is a 0 or a 1, but before that it's in a superposition. So what Einstein said was that this cannot be true. All measurement outcomes are predetermined. So there's some hidden variable that tells you whether the qubit is 0 or 1. And also information cannot travel faster than the speed of light. So both things are local realism. Show you in the next slide that local realism implies that S can be at most 2. But I also said that quantum mechanics gives you S equal to 2 square root of 2, which is bigger than 2. So what does that mean? That means that local realism cannot be true. But if local realism is not true, then either 1 is not true or 2 is not true, right? Or both are not true. So now physicists assume that 2 is still true. Information can go at most at the speed of light. So if 2 is true, that means that 1 has to be false. So indeed, measurement outcomes are not predetermined. Their nature is probabilistic. Okay, so let's go through the proof found on S. So this gets kind of technical. I will go through it quickly, but you can read in the lecture notes if you want to know more details. So the hidden variables, we go by lambda. And basically what these lambdas say is what Alice and Bob, what they will give as output, given input 0 or 1. So for instance, A lambda 0, that tells you what Alice's output will be, given that she gets a 0 as an input, and given the hidden variable lambda. So the hidden variable covers the source, the strategies of Alice and Bob, and basically the entire universe. And given that, given the hidden variable lambda and the input, output of Alice and Bob is fixed. Basically what this is. So then if we calculate one of these S, or one of these 4 S's, you can sum over all the different hidden variables. With PL is the probability of them using that hidden variable. And then A times B, so this is the average of A times B for all rounds. Yeah, you can do something similar for all four of these S values, and then you get this for the total S value. And then you can rewrite this term, these four terms, you can rewrite as like this. And then when you think about it, you can, there are basically 16 different possibilities for choosing these four numbers. 2 times 2 times 2 times 2 is 16, so 16 possibilities. And if you plug all those possibilities in, you will see it's always between -2 and 2. But we take the average of this number. So the average will also be between -2. That's basically the proof. Now, how do you use quantum mechanics to get a likelihood value for that? This will be a tutorial exercise this afternoon, so you can work it out yourself. It involves a lot of calculations. But basically, the experiment involves this interesting superposition 0, 0, 1, 1. Right? This will ensure that they will get the same input every time. So in the experiment, the source is giving the first qubit to Alice and the second to Bob. That is what the source is doing. So the source is distributing this two qubit states. Then Alice and Bob perform a measurement on their qubit. And as you may know from previous lectures, if you do a measurement on a qubit, you can use different bases to measure it. So the normal basis is 0, 1. You can also have plus or minus, the plus minus basis, the Hadamard basis, but you can have any other basis, which you can also denote by an angle. This is a graphical picture of the different bases and colors. So what happens is Alice has two different basis measurements, two different bases that she can measure in. And depending on the input 0 or 1 she gets, she will choose either the 0, 1 basis or the plus minus basis. And the same for Bob. He has two different bases. And depending on his input, he will choose either the first one or the second one. And then they will form the measurement on the qubit they get in that basis. And then basically what you can show is that the S value you get is 2 squared of 2. And to do that, you have to use Born's rule. So you might have to look this up in the lecture notes if you want to do this exercise later. It's quite fun. So Born's rule, for instance, if you want to know the probability that Alice and Bob both give +1, given that X and Y, the inputs are 0, 0, you would have to calculate something like this. So here we have the states, the input state by plus. If Alice gets input, so Alice gets output +1. In the case that she has input 0, so we're in this case, so we use this 0. That's why there's a 0 here. And then if Bob has outputs of +1 and he has input 0, so that means that we have to use this one, pi/8, and that's why there's a pi/8 here. Take the inner product and you square it. This is Born's rule. You have to do a lot of calculations like this, and then you will find that the S value is 2 squared of 2, which is greater than 2. So that means we can do an experiment, which was actually done in 1982, which shows that S is greater than 2. It means that local realism is not true, which means that that nature is probabilistic, that indeed some values that you can measure are not predetermined. They only assume the value when you do the measurement. It's very counterintuitive. Yeah, the experiment shows that it's true. So there were some loopholes in this experiment in 1982. For instance, you really have to make sure that Alice and Bob don't learn the input of the other. This is quite hard. So the first loop-free experiment was only quite recently. It was in 2015 by 3 different groups around the world. They did the same experiment, and they showed they had an S value that was close to 2 squared of 2. So conclusion, nature is probabilistic. And I think, yeah, there are a couple of interesting consequences. So it's very philosophical, right? Because it's so weird that you have something and then it's in a superposition. You can only when you measure it, it assumes a value. It's very different than any that we know. You cannot come up with any classical thing that we have in real life where something like this happens. Even if you were to throw a form, you might think that that is probabilistic. But still, if you know exactly how, with which speed and with angle you throw this coin, then you can actually calculate how it will fall and if it will be heads or tails. In principle, you could do that. So it's not really probabilistic throwing this coin. But quantum mechanics is really probabilistic. It is not predetermined. You cannot calculate if it will be heads or tails, or if the qubit will be 0 or 1. It's also a confirmation of quantum mechanics because quantum mechanics predicts its future, and the experiment shows that it's true. So that means the theory is true. And as you will see later, Enrique will give you a lecture about quantum key distribution, which is some cryptographic scheme that makes use of this. Yeah, we'll learn about that later. And that was it.